to what I call the real Jordan form. So the real Jordan form allows for things like rotation matrices. Still haven't told you what a Jordan form is. To explain that, I should tell you about blocks. We've talked about blocks before, but there's this construction, A direct sum B. I don't know if I've talked about that in here, maybe not. The direct sum of the matrix A and the matrix B is a block diagonal matrix like this. So here I'm assuming that A and B are square, but they don't have to be the same size. A could be 2 by 2, B could be 5 by 5, whatever. This still makes sense. So A direct sum B is a block diagonal matrix with blocks A and B. So the Jordan form. What is a Jordan form? Jordan form is direct sum of Jordan blocks. Begging the question, what is a Jordan block? All right, well, let's start out at the beginning. It's a very good place to start, right? J1, lambda. This is extremely silly. This is the 1 by 1 Jordan block. It is just lambda, a 1 by 1 matrix. What is the second Jordan block, J2? You got yourself a lambda and a 1 on the super diagonal. I can tell you already, I'm not going to have time to tell you about the real Jordan form today. I'll tell you about this real Jordan form another day. The real Jordan form is actually sort of the more responsible thing to teach you guys because you're interested in real calculations, right? Real world applications that are built from real variables. And to be totally general, you need this real Jordan form. This covers all possibilities. Every real matrix is similar to a real Jordan form. In some sense, this is like the skeleton of a real matrix. It's what is fundamental to making it what it is. Yep.
What's the word similar?
I had it defined over here. Okay. It was the P inverse AP. Oh, yeah. B is equal to P inverse AP. Now, what that actually means is that I can find a basis and make a basis matrix such that the basis matrix inverse times A times the basis matrix again gets me to that similar matrix. What do you think J3 is? Lambda, lambda, lambda? Yeah. And then 1's on the super diagonal. What is J4? Lambda, 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 lambda. 1's on the super diagonal. 0's elsewhere. Do I need to write J5? Okay. So the D, in our example, we had D was what was it? Was 1 and 0 and 0, 3. So that was actually a Jordan form. Jordan form is the generalization of a diagonalizable matrix. It's the next best thing to diagonalizable when we can't have diagonalizable. But it includes diagonalizable matrices as a special case. This is J1, 1, direct sum, J1, 3. Silly, but true. Diagonal matrices are Jordan form. But the converse is not necessarily true. Okay? Like, it is impossible. Fact. Okay? 2, 1, 0, 2, this matrix is not similar to, is not diagonalizable. The proof of this relies on a simple statement. similar matrices have the same Jordan form up to the ordering of the blocks. What's the Jordan form of a diagonalizable matrix? It's the diagonalized version of the matrix, right? What's the Jordan form of that matrix? Trick question. I mean, this is J22, right? That is its Jordan form. That matrix is not diagonalizable. Can't do it. Yeah, I mean, you can't get an eigenbasis for that matrix. You have to get what's called a generalized eigenbasis, or what's also known as a Jordan basis, not surprisingly. And the way to form this Jordan basis is from unioning together what are called Jordan chains. I should talk about this as it relates to differential equations. It turns out to solve the differential equation, this one right here, in the case that you have generalized eigenvectors, in the case that you have a system which is based on a matrix which is not diagonalizable, you really need the Jordan form, the Jordan basis really, the eigenbasis, generalized eigenbasis in order to solve it. It'll take me like a half hour to really explain that properly. I'll do it some other day, obviously. But anyway, one last example and we'll stop for today. Try to make it a simple one here. Let's get back. We'll come back to Jordan form another day. I mean, the answer to your question is involved, is my point. The diagonalizable case is the most interesting and exciting and simple case. We try to focus a lot of our energy there, all right? But here's one. If I have q of xy equals to 8xy plus y squared, this is called a quadratic form, right? I can write this as a matrix. So this is actually the matrix x comma y, that's a row vector, times some 2 by 2 matrix times xy. Now if we're smart, we'll make this symmetric so we can apply the real spectral theorem. So to make this symmetric, what I do, it's got 0x squared, it's got 1y squared. How do I get the 8xy term? Well, I put a 4 here, and I put a 4 there. I'll talk about this more another day. If you don't follow yet, it's okay. But anyway, there's the matrix A, and then let's find the eigenvalues of this thing. So the determinant of A minus lambda I is the determinant minus lambda 4, 4, 1 minus lambda, which is what? Lambda squared minus lambda minus 16. Ain't pretty. But this is lambda minus 1/2 quantity squared plus a fourth minus, 64 over 4, yeah? So that's lambda minus 1/2 squared minus 63 over 4. So I can tell you that lambda is equal to 1/2 plus or minus the square root of 63 over 2. The real spectral theorem said what? It said that A is equal to lambda 1 U1 U1 transpose plus lambda 2 U2 U2 transpose, where U1 and U2 are an orthonormal eigenbasis corresponding to the eigenvalues 1 plus or minus the square root of 63 over 2. Right? Well, I'm out of time, so let me just kind of jump to, let me flesh out the details of this next time, but just give you the punchline right now. So, long story short, I will show you explicitly that we can find coordinates, x bar and y bar, such that this is lambda 1 x bar squared plus lambda 2 y bar squared. In other words, there's a coordinate system where this is just, 1 plus the square root of 63 over 2 x bar squared plus 1 minus the square root of 63 over 2 y bar squared, right? So if I told you to look at the equation, this equals to 1, and I asked you geometrically, what is this thing right here? Like, what is that geometrically? It's not obvious what it is it? Is it an ellipse? Is it a circle? Is it a hyperbola? I don't know. Could be any of those things. It's a quadratic form. But this right here, if I set this equal to 1, this is positive. This is not. Square root of 63 is 7 point something or other. That's bigger than 1. This is positive. This is negative. If I have something squared minus something else squared, that's a hyperbola. So the Eigen coordinates are rotated. It's a rotated coordinate system which reveals what this quadratic form actually is. Some of your homework problems are about this. Again, it's about finding eigenvectors and eigenvalues and interpreting them. No need for Jordan form here. Not really. Thankfully. You're like, quadratic forms, who cares? Oh, you should care. Quadratic forms are so many things. Like the inertia tensor in classical mechanics is a quadratic form. That describes, well, anyway, I shut up. Enough for today. I'm sorry. Yep.
We have irreducible. We have irreducible reals, and we have irreducible complexes. Irreducible complexes.
Well, that's the beautiful thing about complex numbers is if I have an nth order complex polynomial, there exist n complex solutions, possibly repeated. So there's always enough eigenvalues in the complexes. There's no such thing as an irreducible quadratic over the complexes. They all split down to real factors. That's the fundamental theorem of algebra.
Okay. Oh, is that your point in saying? I was just wondering, because you said
irreducible. Yeah, that means this can't be factored with real numbers.
Okay.
Yeah. That is an interesting question. Like in the rational numbers, you can find rational polynomials of arbitrarily high degree which don't factor over the rationals. And so in the rational numbers, this is not really a very good approach. You need something called the rational canonical form, which gives you blocks corresponding to arbitrary degree irreducible polynomials. If you want to know more about this, please come take Math 422.
Okay. And also, is
Oh.
is an eigenbasis like a sort of like a subset of like a Jordan basis then? Since the Jordan
Yes, an
generalized?
eigenbasis is a special case of a Jordan basis, right? It's a Jordan basis where all the chains have length 1.
Jordan has chains of all length.
Chains of length 1. Yeah, we'll talk about these chains another day. Yeah. If your head feels like it's